All right, so we're going to start to talk about this next process here. Not using common interval. But we still are going to be using these ideas from the purpose of statistics and the process of statistics. So how this works is that we want to quote unquote prove a difference. Now, why would we say that we want to prove a difference? Well, based on the purpose of statistics, we have variation, right? So variation means that we can't prove equality. If somebody says to you, well, I think the average age of people in a class would be 27. And you say, well, you can't say that. You can't say that it's equal to something because samples are always varying. The ages are always changing. So there's no way that you can say, I can prove that the average of ages in a certain place are a certain number, because you can't, because there's too much variation. However, if somebody says to you, I think the ages of this particular class are higher than average, and you find out that the average is 40 when you thought it was going to be 25, then you're like, oh, well, that's really different. That's very different between them. So you say, okay, I can't prove that two things are the same, but I can certainly consider if two things are very different, then there's reasons why, okay? But then the other thing that happens is that because we're doing this process of statistics, we're just taking samples and we're talking about the population, then we have a, we're going to use our statistics in figuring the probability of the difference. So the basic idea here is that we're going to set up a situation where we say, how different is this compared to some other standard number that I have? And then based on that information, then we're going to say it is different, or I can't prove that it's different. Okay. Now this will hopefully become more clear as we go. All right. So let's take an example, and I'm kind of always connected to politics, but maybe we should do something like health. All right, so let's say that I've got 500 people, and 15% report dizziness. And let's say these 500 people were all taking an antihistamine. Right. 500 people, they're taking antihistamine, 15% of them report dizziness after taking this thing. But if we say that we have a general survey where 10% report dizziness. Question. Is our group higher in the proportion of dizziness? Okay. So we say normally only 10% of people would report dizziness, but these people that are taking the antihistamine, it's 15%. Is that significantly different? Okay. And what I'm going to tell to you next is very important. I want to make sure you understand that when we get to the end of the process, we have two options. I want you to know these options. I want you to write these things down, okay? The first option is that we prove the difference okay? And so then we say there is evidence to prove the difference. And in parentheses, I say this is our goal. This is what I want to happen. But sometimes it doesn't happen, okay? If I'm over here, okay, then what I'm going to say is no decision. I'm going to say there is not enough evidence to prove the difference. And then in parentheses, I'm going to say it could be a random variation. This is a pretty big deal. I really want you to know this, because this is what happens at the end of the problem. You want to make a summary of your conclusion. You want to say, well, what does this actually mean? And the goal of hypothesis testing is that we want to prove a difference. If we can, that's good. And then we say there's evidence of this. We can't say for sure 100% that it is that way. We're just saying, I just did a study here and I have evidence that it is that way. And that's what we want to do. We want to say, it looks that way to me right now. But sometimes it doesn't work, because sometimes the difference between our number and the other number could be just based on, I'm taking a sample and samples change. And so then I say, I can't make a decision. I can't say that there is a substantial difference here. So I say there is not enough evidence to prove the difference, because it could just be that it was by chance. I just happened to make this happen because of the people that I picked, the 500 people, whatever. Okay, so what I'm going to hand to you now is the steps for hypothesis testing, along with some other information. And this is out on Blackboard as well, but I want you to be able to refer to this all the time. What's going to happen is that from here on out, I'm going to say to you, do you have this sheet of paper in front of you? And you should say yes. And not lie. You should actually have it in front. Yeah. Besides, we're just getting big population. I got it today.
We need one more.
He's probably got one. You have an extra? Okay. Now, what I'm going to do is I'm going to go through and play the videos that are in Blackboard, but they're not in the video section, they're in the notes section. These are videos I made a few years ago now to describe hypothesis testing. We're going to go through this and hope it makes sense. And I'm not sure the volume is going to be good, but we'll see. Introduction to the concept. Why are you not doing anything? It's not muted. Where is all my volume here? I'm at 100%. It's going.
All right.
There I am.
So the question that we're talking about in hypothesis testing is how are we going to make decisions? Consider this idea. Do students at Western own cats more than the national proportion? So we're talking about how many cats do people normally own? And surveys out there say about 30%. And so I want to know, what about students at Western? Do they own more cats than that? So then, how am I going to prove that? Well, I have a problem, okay, if I'm going to try to prove that, because I know that samples are not accurate, right? So that if I take a sample and I say, well, I did a survey and I found out that it was 40%. Well, that doesn't prove anything. It doesn't prove that it's different because it's a sample, right? Because we've talked about sampling variation. Sampling variation tells us we cannot prove anything directly by just looking at samples. But what we can do is we can think about that sampling variation because we know that sampling variation has a distribution, right? And we know that if our sample size is large enough, the sampling distribution is going to be bell-shaped. And so then we can control, or we can understand what might happen, because when we do samples, we can know how much variation is going to be in our samples. So then we can actually figure out what to expect from a sample. Now, what the logic of hypothesis testing goes like this. If we get an unusual result, that means that then our assumption about population may be wrong. So I'm looking at my sample. I say, all right, I've got variation in my sample, and I can expect that, right? But if something happens which is unusual, then maybe there's something going on with my assumption. Remember, when we talked about this, we assume the population and the sample distribution have the same mean, okay? But if we get some kind of an unusual result, it's like, oh, wait a minute, that may not be right. Let me give you an example here. Consider that this idea, do students own cats more than the national proportion? The national proportion is about 30%. So if I say that the national proportion is 30%, and yet I get a sample which is out here at 40%, then I look at that and I say, well, wait a minute. If there's a large, significant difference here between these, then that means the meaning of that measurement. It could be that what I'm measuring is not actually from that population. That with Western students, when I took that sample, they don't have a proportion of 30% cat ownership. And so that is why my sample was so high at 40%. So what I'm looking for is unusual results, which will then tell me that where I got my sample is not the same as the assumption that I had made. Okay, I'll come back to that in just a minute. But that is the basics of hypothesis testing.
All right, so to show you a little bit, whoa, don't do that. To show you a little bit of what this looks like. Remember, we said if I know my population has a certain distribution here, then I know my sample would also have a distribution which will have the same mean that this does. But if my sample number is way up here, then maybe what I'm thinking about my population is not actually correct. But again, when we go back to the process of statistics, I don't just care about these 500 people taking antihistamines. What I want to say is, in general, everybody taking antihistamines, are they more prone to dizziness than the general public? And so I'm not just asking, is 15 greater than 10? I know it is. The question is, does the population of people taking antihistamines, do I have evidence that that number for the population is higher than the 10%? All right, so we'll go to the next video here, part 2. Now I changed the way that I recorded the audio, so the audio is a little different, but here we go.
All right, so we talked about hypothesis testing, what it is. Now we're going to get into the nitty-gritty details. So in order to make this work, we have some traditional views, traditional ideas of what hypothesis testing is all about. And so we start with describing our basic assumption, which is the null hypothesis. The null hypothesis is our standard. We set a standard and we say, assume this to be true. So the null hypothesis is going to have an equal sign in it. And so it's an H with a subscript 0. Null hypothesis, which is saying to us, this is our assumption. It can be either about mean, or about a proportion, or about a standard deviation, right? Those are the 3 things we've been working with here. And then we have the question of what is it that we're trying to prove? Very important to understand. What we're trying to prove is called an alternative hypothesis. We cannot prove the null hypothesis. We cannot ever prove from a sample that we have something equal to a number, right? Like we said, you can't do that. A sample is not accurate, so you cannot prove equality. But What we can do, this is the power of hypothesis testing, is that we can prove a difference. We can say, with a certain amount of confidence, the population measurement is either greater than or less than the number, some kind of standard number that's been set for us. Now, it's generally, when we're talking about these things, we're talking about alternative hypothesis as being different from the null hypothesis. Then that means we're looking at the tails. If we're looking for the sample as being higher than a certain number, that would be a right tail. If it's lower than a certain number, that would be a left tail. And it is possible sometimes if we don't know what we're doing as far as either less than or greater, we'll say it's two-tailed. It's a two-tailed test. I don't like two-tailed tests. I'm strange compared to other teachers maybe, but I just don't like it. Because if we have the sample information, then we know something about what direction we're going. So what I give you will be one-tailed tests. Now, of course, when we say we're going to do a test, then we can adjust how confident we want to be in it, just like with confidence intervals. So we can say, all right, I'm going to pick alpha. My chance of being wrong, and most of the time it's 5%, 0.05. But we pick that, right? And so then we have the tail. If you have the distribution and then you have the tail and it's got an alpha in it, that place out there, that's called the rejection region or the critical region.
Okay, I'm just going to show you what that looks like here. If it's a left-tailed test, then it will look like this. This is going to be alpha. And then this place right here, this interval is called the rejection region. And then if it's a right-tailed test, look like this. This is be where alpha is, and then this interval is the rejection region. And again, there are a few times in the textbook where they'll talk about two-tailed tests, and we won't have very many of those, but it could happen.
So this is what we're saying, is that if the sample comes out to be in that place out there, in that tail, then we've found the place. We've found the difference. It is significantly different if it's out there in the tail, if it's in that rejection region. And so then that's how we set this up. We're going to set up the hypotheses. We're going to be trying to prove the alternative. We're going to be looking for where the tail is. And then we're going to use some kind of equation or formula to say, all right, is it out there? Is it in that tail? And then once we get it out there, if it's out there, then we say we reject the null hypothesis. That's the goal. We want to reject the null hypothesis because that means we've proven something. We prove that there's a difference. Well then.
Okay, so I'm going to stop that just so you can think about it here. I'm going to have a rejection region, either on the left-hand side or the right-hand side. And that would be the place where I would say, if my number from my sample ends up way out here compared to where I thought it would be, then there's a difference from my group compared to the other group. So then this thing where I had proved the difference, this is going to be reject. Marker. Reject the marker. I can't hit the trash can from here. All right. Reject H0. That is where I'm going to reject the idea of the standard value that I started with. Then this over here becomes do not reject H0. Now, most people, when they say reject, think of it as being, I'm getting rid of a bad thing. However, in statistics, when we reject the null hypothesis, that means we've proven the difference. That means there is evidence, and that is what we want to do. We want to reject the null hypothesis in order to prove the difference. Most students, when they get to a certain place, they say, reject it. And I say every time, no, it's not reject it. If you want to reject the null hypothesis, that's what you say. Reject the null hypothesis, prove the difference. Rejection normally is bad, but here, rejection is what we want. We want to reject the null hypothesis to prove the difference. On the other side, we say do not reject, but then that means we do not make a decision. We don't know the answer when we do not reject the null hypothesis. All right, we'll come back to that.
Okay, this is where a lot of people have trouble, all right? If you do not reject the null hypothesis, you have not proven anything. So we have two alternative choices when we get down to the end. Either we reject the null hypothesis or we do not make a decision. We can never prove that equal sign. We can never prove that something is the same as a certain standard. So either we prove it's different, we reject the null hypothesis, or no decision. Those are the two possible options. So I'll come back and talk about more. But that is the idea of the main steps for hypothesis testing.
All right. So now we go to part 3. Another audio change.
We're talking about hypothesis testing. There's some more details that I still haven't fully gotten out there for you. And I'm going to actually go through the example of the cat ownership and show you exactly how this whole thing works. Now, there are these specific steps. This is listed on your laminated sheets as well as in the textbook. These 5 steps
And it's on your sheet
of
paper.
how hypothesis testing actually works. We'll go through them in detail. There's a couple of new things here. The idea of the critical value and the test value. But first of all, here's the question. Here we have this survey. Do you have a cat in your household? So we have 40 out of 100 that say yes. Of course, that's 40%. Now we want to say, is this actually higher than the national survey of 30%? How we're going to pick 0.05. So, as we talked about in the earlier ones, we've got the null hypothesis. That's the standard we're setting. The 30% is the standard. And then we want to prove that what we've got for the students that we surveyed is that they're not part of that population. They have a greater value.
All right. Notice, please, that when we say what is the hypothesis is not a number. The hypothesis is a statement. The hypothesis is that the proportion is equal to 30%. So that when it comes test time and I say write the hypothesis, it'll be a statement about the proportion, mean, or standard deviation. The alternative hypothesis is also a statement about the proportion. The alternative hypothesis says P is greater than 30%. It is not just a number, it is a statement. The alternative hypothesis is saying this is what we want to prove. We want to prove that Western students have a higher proportion than this national number. Notice, this is not P hat. I'm not trying to prove something about my sample. I already know my sample number is 40%. What I want to prove is that all of the Western students have a proportion greater than 30%. Even though I only talked to 100, I want to know, is that sufficient evidence to prove that the population number for Western is higher than 30? That's what I want. All right. A little punctuation on my statement there, that's fine.
Now, what is the critical value? Well, it's the number which tells us where alpha lives, okay? And if we're looking for alpha 0.05, then we can look that up on the table and find that that means the critical value is 1.645. Anything greater than that would be an unusual result.
Okay, where is that? Where do I find that critical value? Where do I find that alpha 0.05 to the right? I could look at table E and try to find 0.05, or I could use table F. You look at table F and go all the way down to the bottom, what do you see? You see z-scores. So if I'm on table F and I go all the way down to the bottom, what am I specifically looking for? I am looking for a one-tailed alpha of 0.05. Most people don't believe me when I say that. Most people want to use the first number of confidence intervals, but this is not a confidence interval. So I am going to ignore that top line which says confidence intervals because I'm not doing a confidence interval now. I'm doing a hypothesis test. So I'm going to look where it says one tail, alpha, 0.05, and I go all the way down to the bottom, 1.645. That's the number I'm going to use for a one-tailed, right-tailed test. That's the cutoff for where alpha is going to be. And you see that in the picture down at the bottom, one tail area over there to the right. So the best option is to use table F in order to find the correct z-score, but make sure that you are using the one-tailed value for alpha. It's not alpha divided by 2 because it's a one-tailed test. That number that we find, 1.645, that's called the critical value. The shaded in part of the graph, that's called the rejection region. Okay, so the critical value is there. The rejection region is now to the right. Okay, so this is step 2 on your sheet. Find the critical value and the rejection region from the appropriate table. All right.
Greater than that would be an unusual result. So we're going to compare then this critical value, that's where alpha is, and we're going to compare it with the test value. test value information is going to come from the sample and also from the statement of the problem. And we're going to get a number that we're going to use. This is
Okay. So the critical value is right here. But step number 3 here is compute the test value. After I compute the test value, then step 4, I'm going to make a decision. I'm going to compare the test value to the critical value and rejection. So I need to find the test value and then decide what to do with it. And I have a formula for the test value.
That's how it works. What is the test value? There's a formula on your sheet, the z-score that we need when we're doing proportions. We take p hat minus p over square root of pq over n. Numbers are listed.
Okay. So I put it on here because I didn't have the software to make it happen. But now I do. Anyway, my test value, z equals p hat minus p divided by square root of pq over n. This is on the important formulas and tables section, but it's also right here. It's also in your textbook. Where do I get p hat? P hat comes from my sample. Where do I get p? This comes from the null hypothesis. This is the number that was given to me as a standard number that I'm comparing. This is p down here also. Q is, of course, 1 minus p, and it's the sample size. Now, if you're thinking carefully, you would say, oh, I remember that z was the data value minus the mean divided by the standard deviation. And that's what's happening here. So what do we have? In our example, our sample number was 40%. The number we're comparing it to was 30%. So then we put 30 and 70 in here, or 0.3, 0.7, and then we had 100 people in the sample. So I figure this all out and I get 2.182. So where am I? My critical value was 1.645. My test value, z is equal to 2.182.
So therefore, we come out with 2.182. So now we can make our decision. If we have this thing in the rejection region, then we're good. We proved it. And that's what happened here. The test value comes out to be 2.182. The critical value is the 1.645. So we're out there. We've done it.
Okay. How do I know what to do? How am I going to make a decision? If the test value is in the rejection region, I reject the null hypothesis. What does that mean? If I reject the null hypothesis, then that means I've proven a difference. This is out farther. It's an unusual event. And so I say there is evidence to prove the difference. And that's what I want to do. I want to say there's evidence for an actual difference, that my sample is not just randomly bigger than 30%, but it's an unusual value, so I say there's something going on here. Western students don't have cat ownership at 30%. It must be higher than that.
Now we want to summarize the results. The long form has all the details about how this works, but then we just want to know what's the short form, right? The true summary.
Okay, on your sheet, you have parts of a conclusion. You have all these different things that are listed on there. You don't need to worry about that right now, okay? We'll talk much more about that down the road. But currently, you just really need to focus on going through the process up to this point, okay? And then making the correct decision at the end of the process. All this stuff, parts of a conclusion, that's bonus right now. It's much more important that you get the basic idea of how this works.
Is it or isn't it? Okay. And so the long form is going to have a lot more details in it. You need to know them both. Okay. Here are all the things in the long form. Now you'll have this list. I'll give this to you so you'll know what the list is. But then, and we're going to do this for the example so you can see how each part of this gives us information that we want to know when we're drawing a conclusion. 95% confidence, there is evidence. That's what we're saying. There is evidence to prove this. And we don't care about the sample. We're asking, what is the population proportion of students? It's greater than that in the national survey. So yeah, we've proved it. That's great. There are only two possible conclusions. Either we proved what we set out to prove, or there's no decision. As you go through the examples, you'll see this. It's important that you understand. Either we proved it, which is a good thing, or we cannot make a decision. Now there's another thing.
Okay, we're not going to do this yet. P-value, that comes later. All right. So, with all this in mind, okay, with all that's happening here, the goal here is that we have to have some kind of a standard number which is given to us. And then we're trying to prove that what we have is not that same thing. It's somehow different than what we were originally given. And then when we go through the process, we can either say, yes, I proved it, or we say, I didn't prove anything, I don't know what's actually going on here. Now compare this to the idea of the confidence interval. The confidence interval tells me where my population number is. This doesn't. All this does is compare two numbers and say, yes, they're different, or no, they're not. And so it's just not that much information. It's generally not that helpful. So that's why people say don't do this. But again, statistical traditions tell us this is what you're supposed to do. All right, so we did the example of the cat ownership. Now I want to take us through this example of the dizziness and see if the dizziness can tell us what we're supposed to do here. So the first step, as it's on our sheet here, is to state the hypotheses and identify the claim. Textbook, I don't agree with how they do it. They say that there's supposed to be a claim somehow here. And we'll talk about what that means in just a minute. But what we're going to have then is the null hypothesis and the alternative hypothesis. So what we're going to write down here is some measurement. And in the first situation, it's equal to something. And then the second one, it's that measurement, but then we have to decide, are we talking about it being greater than or less than? The number that we're going to put in here for both of these hypotheses is the standard number that we were given. In this case, 10%. What's happening here is that we're assuming that our group is the same as the general public, and then to see if that's a good assumption to make. So then the null hypothesis is that our group is equal to 10. And then the alternative from what we have would be that our group is greater than 10%. That people who take this antihistamine have more dizziness than the general public. So this is our first step, stating the hypotheses. Now, when we say identify the claim, most of the time, right, people are claiming that there is a difference. So when we see this, we say, hey, it looks to me like there's more people that have dizziness. Once in a great while, the textbook throws a curve and says, oh, well, we're claiming that it's equal to this. And I think it's just messed up when you say, well, which one is the claim? You look at the problem and you say, the person says it's greater than, that's the claim. If the person says it's equal to, that's the claim. But the only thing we're actually able to prove is the alternative, H1. We can only prove the difference. All right, so then, step 2, we want the critical value and the rejection region from the appropriate table. So let's just make this a little bit different. Let's choose alpha to be 99%, or I'm sorry, 0.01. I want to really be sure that these people are different. I don't want to just make a claim. I want to be really sure about what I say. So I'm choosing alpha to be 0.01. So then, based on that, I need to find the critical value and the rejection region. And I'm going to look at the table. And I'm going to use the z-score table. Well, I'm going to use table F all the way down to the bottom. What do I see? I want one tail, 0.01. 2.326 is the number. So that will be here, 2.326. And then anything beyond that would be in my rejection. So I'm looking at table F. I look at the one tail row. I go over to where it says 0.01. I go all the way down to the bottom, 2.326. I don't use the confidence interval numbers because this is not a confidence interval. It's a hypothesis test, and it's one tail. What would happen if I wanted to do a left-tailed test? This would be a negative 2.326. So when I look at these numbers, they're all positive numbers. But if I'm on the left side of my z, then it's negative. So I'm done with step 1. I'm done with step 2. I found the critical value, the rejection region. Now I need to compute the test value. My formula for test value is p hat minus P divided by square root of PQ over N. P hat comes from my sample, so that's going to be 0.15. P without the hat, hatless P, is 0.10. So this is 0.1, 0.9, 500. So I need to put those things into my formula and find out what they are.
How is it 0.1 and not 0.0?
This is the number from the null hypothesis.
Sorry, on the bottom. What's the
Is
0.1?
Liz, tell me you got a number for me? Okay. Mariah, you got a number?
Not quite there yet.
Okay. Lena Miller, you got a number?
Almost.
Gabrielle, you got a number?
How many?
I want 3 decimal places.
Okay, 3.727.
3.727. You ready for this one? That's not one. Okay, so hopefully that's what you get. Now, what does it mean? We computed the test value, step 3. Now, step 4, we want to make the decision to reject or not reject the null hypothesis. Okay? How do we decide? Well, I'm going to find out, is the test value in the rejection region? The answer is yes. 3.727 is out here. It's beyond the critical value. It's in the rejection region. So the test value is in the rejection region. So what do I do? I am going to reject the null hypothesis. So, Jessica, is that a bad thing or a good thing?
It's a good thing, 'cause it's a problem.
It's a good thing, what?
It's a good thing, 'cause that's what we want.
Okay, that's what we want, so it's a good thing. We wanted to reject the null hypothesis because now we can summarize our results. We won't go through the long version. We'll just summarize our results and say, if I reject the null hypothesis, that means there is evidence for a difference. What difference am I talking about? I'm talking about the difference of the antihistamine taking people versus the general ones. So what I have now done, whether I wanted to in the larger sense is different. But if I'm going to use numbers like this, then I'm going to be able to say I can prove a difference. I can show that people taking the antihistamines have a higher rate of dizziness compared to the general. Okay, so the difference becomes people taking antihistamines have more dizziness. And I don't know if it's supposed to be a Y or an I there, but I just put an I. Dizziness. I don't actually know what that dizziness rate is. The only thing I know right now is that it's higher than 10%. When I had the 15, that wasn't an actual number, it was just a sample. But it would be unusual to get a sample of 15 if the actual population was 10. So I'm looking at this and I'm saying, well, it's out there. It's way different. Different enough so that I say, there's something going on here. I assumed they were the same as the general, but they're not, because there would be a low chance of me getting that number 15 when it's supposed to be 10. But the only way I can know that is by actually putting it into this formula and comparing my test value to my critical value. Okay. Now, what would happen if instead of having 500 people, I only had 100 people? So I'm going to change this now, and I'm going to say everything else is true, but I only had 100 people, and they're reporting dizziness. And 15% said, yes, we are. What changes? I still have the same known alternative hypothesis. I'm going to use the same alpha, but what's going to change is my test value. I'm now going to change this so that it has a 100 on the bottom instead of a 500. Crystal Reed, you got anything for me?
Do you want the answer?
I do.
1.667.
Okay, 1.667. So now, if I look at this number, and I say, what happens now? My test value is not in the rejection region. So what do I say? Test value not in rejection region. I do not reject the null hypothesis. What happens when I do not reject the null hypothesis? Then I say there is not, or perhaps better, there is not enough evidence for a difference. So then what do I actually say at the end of the problem? I say no decision. Listen.
So is your rejection area the shaded part?
Yes.
Okay. So if it does fall in there, then you reject the,
No hypothesis. Here it's not in there, so I do not reject the null hypothesis. So what I say is there is not enough evidence to prove a difference. So this 15% could have just been a fluctuation. It could have just been part of the variation of taking samples. I can't actually say that my group is different from the general population. Even though 15 is different from 10, it's not sufficiently different based on my sample size. Remember that if you have a larger sample size, your variation is smaller. Well, if you have a small sample size, your variation is greater. So I can't prove anything here. Hopefully this makes it clear to you. You want larger sample sizes, okay? You want to be able to prove things. If your sample sizes are too small, you just can't prove anything. Now, this creates a real problem. Because if somebody goes through and they spend a couple of years trying to prove something, and they get down to the end and they get all their data and there's nothing there, are they going to publish that in a major research thing? I didn't find anything. Turns out, no. Most of the time, people don't actually publish the fact that they didn't find any evidence. Because people want to prove things. They don't want to say, I couldn't find any evidence for this. So what happens is when you read these journals that are out there, they don't tell you when there's not evidence for stuff. And so it's biased in favor of things being proven. Even though, in reality, most things aren't. So then when you say, hey, guess what? I want to prove something. And you go out there and you say, there's nothing there. That's what happened, okay? Now, there's also a problem. I'll give you an example. What happens when cars come up to a stoplight and they want to turn right on red?
Well, they stop and they have to wait.
They can go, but they have to wait, right? Do you think it's going to cause more pedestrian accidents if you allow people to turn right on red? Well, the research was done for a couple of years before they changed the law. And they said, well, we couldn't find evidence that it changed anything. The reason why? Because their sample sizes were small. Because it wasn't the law everywhere. It was just in a couple of different places. And those places saw maybe a little bit of an increase, but it wasn't sufficient in order for them to prove for sure. Well, then it became the law everywhere. And guess what? Yeah, it does. It does cause more pedestrian accidents because when you turn right on red, you're looking over there at all this traffic and you're not looking over here at the pedestrian. So it creates more accidents when you do that. But as a society, we've decided, well, we're just going to do it because we like it. So we do. Even though there's a risk, we're willing to run that risk because we don't want to sit there at the stoplight when I could be turning right. Come on. So you can have like 20 studies and they can all say we didn't find any evidence. And then when you put them all together, they did. So it all depends on the sample size. Question?
So does this mean that like, there's always gonna be a big enough sample size that it will always prove it?
Not always, no. Because, let me put it to you this way. I'm gonna explain it this way, all right? If you had a large enough sample size, you might actually find a difference, but the difference might not matter, right? So then if I say, okay, is it 15% versus 10%? You might say, well, that makes a difference. But what if it's 15% versus 14.9%? It's like, well, that doesn't matter. But if I have 2 million people in my sample, I can prove that it's actually different. It's higher, 15% versus 14.9. Well, that doesn't matter. So yes, you're right that if we have a large enough sample size, we can prove a difference. But the question is, well, is that difference actually meaningful or not? And we don't know that without having some experience and understanding the situation. All right, that's enough for us for today. So hope you have a good weekend. I'll plan to see you on Tuesday.
Are we getting our test back?
Yes. Well, I might have your grades. I'm not sure I'm going to hand them back, but I'll have your grades.
Thank you.